Log on, tune in, find out. Another good idea from Cambridge.
Who will start his series on higher representations of Lie algebras.
Okay, thank you. So I'll give a quick survey of what I will be discussing. Oh, well, okay, there's some bits here. Okay, yeah. So what I would like to describe is how to develop some kind of higher version of representation theory. So representation theory, that's groups or algebras acting on vector spaces. And you can upgrade the categorical level and call two representation theory. So study now not just of groups or algebras or monoids, but of monoidal categories, possibly with some extra structure. If I want some kind of linearities, maybe some kind of abelian categories, maybe triangulated. So that, and you can consider that question. So it's not clear why you would want to do that. So there is a relation between the two. That's the usual categorification philosophy. Which is better understood as in terms of decategorification, that if you have an abelian category or a triangulated category, you can take its Grothendieck group and you get an abelian group. And if you transfer by a field, you get a vector space. So there is a so-called decategorification. So more precisely, if you have a monoidal category A, such a monoidal category, acting on a category, that means you're given a functor from your monoidal category A to the category of functors from V to V. So A here is monoidal. V, there is an abelian category. And you look at monoidal functors. So whenever you have an object of your category A, you consider a functor from V to V. And if you have a natural transformation, if you have a morphism between two objects of A, you should be given a natural transformation between the functors. So that's the kind of data. We're dealing with abelian categories and want to talk about Grothendieck groups, so we better talk about exact functors. So now that's really what I want to consider as a basic situation of two representation theory. And when you have such a data, some kind of two action of A on V, then you get an ordinary representation. So if you define, say, A, the monoid with objects, the objects of A modulo isomorphisms. So A is a monoidal category, so you can take tensor products of objects. And so isomorphism classes of objects form a monoid. V is an abelian category, so if you put V to be, say, C tensor, the Grothendieck group of V, you get a vector space. And because the functors associated with objects of curly A are exact functors, they induce maps, linear maps on the level of the Grothendieck group. So from this you get a map from A to, there's the homomorphism NC of V. You get a representation of your monoid. So there's this process starting from some kind of higher categorical data. You do get a classical representation. So that's classical thing you might want to do. So representation theory works really well because there is a huge supply of examples, of interesting examples. If you take a random infinite group or random say finite dimensional algebra or infinite dimensional algebra, chances are there's not much you'll be able to say, not much interesting things you'll be able to say about representation theory. And I mean the same would be true here if you take a random monoidal category. It's probably not going to lead to a very interesting true representation theory. So what makes representation theory interesting is that there are a lot of important examples, and studying the representation theory of, say, algebraic groups, finite groups, all kind of hyperalgebras, etc., is important for understanding those groups, etc. So there's something similar going on for true representation theory, and that's what I would like to. Part of that is what I would like to explain. So, key point is that there are interesting examples. There are interesting examples. There are examples of monoidal categories with interesting true representation theory. That's basically that's one important point of my lectures. And interesting means that there's a nice theory, but it's also useful to solve problems which do not involve. It's not just for fun that you want to look at monoidal categories, two categories, etc. And so what I will be discussing in the example in this series of lectures is a class of monoidal categories associated to Kac-Moody algebras. So if you take G, it's a Kac-Moody algebra. You can associate a monoidal category, AG. It's slightly more complicated, but that's basically basic idea. So in the lectures, I will construct this and explain how the representation theory behaves very much like the representation theory of Kac-Moody algebras, and I will explain how it relates to canonical basis quantum groups on one hand and to the geometry of quiver varieties in the other hand. So in the lecture last week of Joe Schwang, you've seen, not in this terminology, but I'll explain the relation, the case of G equal SL2. And the theory in that case is a very it's quite complete. There are structural results, etc. And it's been useful, as you saw last week, to solve questions about representations of symmetry groups, conjectures of Brouet on equivalences of derived categories. So it's only by constructing this very complicated framework that these questions could be solved. So now I would like to explain how you go from SL2 to a general Kac-Moody algebra. So there is not, I mean, it's not so different. And the only difference is the kind of Haker algebras you need to use. You need to use that classical Haker algebras, like affine Haker algebras, or degenerate affine Haker algebras of type A. You need to look at them in a slightly different way. And I think that's what Sasha Kletchev told you about last week. So somehow there are in my lectures, the two main ingredients are the case of SL2 and playing a little bit with Hecke algebras. So I will start with Hecke algebras today, and then I will move to categorical constructions tomorrow. Okay, so the reason why these Hecke algebras, I want to start with Hecke algebras is that they are important to define the maps in those categories I want to define. And in categories, maps are more important than objects, so it's really what one should do first. Okay, so the first section is will be about Hecke algebras. So I will fix K commutative rings and Noetherian. You might take K to be complex numbers if you prefer. That make big difference. And so the data classically of when you deal with Kac-Moody algebras, complex semi-simple algebras, you start with a Dynkin diagram or Cartan matrix. So here the data is some kind of Cartan matrix, but there's more than just a Cartan matrix. So I will start with I, a set that I will take finite. If you can take it to be finite if you're more comfortable, but definition will make sense for infinite sets. And so the data to define these Hecke algebras is a matrix. So it's a matrix of two variable polynomials. So instead of just having a Cartan matrix where the entries would be scalars, integers, the entries are two variable polynomials. And I will put the assumption that QAI is 0. If you think of Cartan matrices, the diagonal terms of a Cartan matrix are equal to 2, so they're not especially interesting. So really interesting information is outside the diagonal. Okay, so associated to such, given such a matrix, you can define an algebra. So we'll define an algebra depending on a parameter n, an integer n. By generator and relations. So you can define it two ways, either by generator and relations or as a subalgebra of endomorphisms of a polynomial ring. So affine, if you're familiar with affine Hecke algebras, they have a faithful polynomial representation. So you can, instead of defining an affine Hecke algebra by generator and relation, you could define it as an algebra of operators acting on polynomials. So you could do the same here. And I will, for what I will do later, generator and relations are more important. But this definition would be much easier to give. But I'd like to start with generator and relation. Okay. So can I use the blackboard on the right? Okay. Okay, so the generators of these algebras, maybe a last piece of notation if you have space here. Yeah. I will denote by L. So nth power of I. So I, typically you would think that I are vertices of a Dynkin diagram. So now I want to think some of a new type of quiver, a new type of graph, where the vertices are going to be given by the set I to the n. Okay, so it's a little bit confusing. The I to the n is really a set of vertex if you want to think of the algebras that I will define as an algebra given by a quiver and relations. Okay, so generators now. There are of three types. You have generators 1 indexed by nu, with nu in I to the n. Second type of generators, just stick to my notations, are x I nu, so x a nu, with a between 1 and n, and nu still in I to the n. And third type of generators are to a nu. A now is between 1 and n minus 1, and nu is in I to the n. So these are the generators. And now there are a few relations. So the first relations are saying that the algebra I'm defining as is given by a quiver, the quotient of a quiver algebra, and the underlying quiver is I to the n. The vertices given by I to the n, so which means really these elements are idempotent. So the first relation is that if you take a product of I nu, 1 nu and 1 nu prime, you get delta nu nu prime 1 nu. That's the second relation, second and third relations are saying that if you think in terms of quivers, so these are corresponding to the vertices, and the x's, they are going to be loops at nu. Okay, so that means if you take 1 nu, you multiply by, or say 1 nu prime x a nu, 1 nu double prime. This is delta nu nu prime nu double prime x a nu. So x is a loop at nu, and now tau is a proper edge. Helps. So tau goes is an edge that is going to go from nu double prime to from nu. Okay, let me write what I want to have. So I need to explain what SA of nu is. So the set I to the n as an action of the symmetric group Sn. And inside Sn, I can consider the transposition A plus 1. So to summarize, so I have a quiver with vertex set I to the n. And the arrows are of the following type. I have x and u's. For every value of a, I have a loop at nu. And I have also an arrow going from nu to SA of nu, which is called tau a nu. Okay, that's expressed by these idempotent. Being by the important one use. So these are the trivial relations having to do with this quiver. So now I need to tell you what are the really interesting relations that you need to put in this quiver. So first relation is that the x's commute. So x a mu times x b nu is x b nu x a nu. Second relation tells you what to do when you want to commute a tau and an x. So there's the sign. I should check that I get the sign. And that's SA of nu. Okay, so you have an edge going from nu to SA of nu, and then a loop at SA of nu. This is a loop at nu, and then you have an edge going from nu to SA of nu. So that is equal to minus 1 nu. Sorry, yes. If A equals B, and SA of nu equals nu, which means that nu A equals nu A plus 1. It's equal to 1 nu if, so now it's A equals B plus, no, B equals A plus 1, and nu A equals nu A plus 1, and it's 0 otherwise. So taus and x's commute unless tau is itself a loop. Tau can be a loop if nu is if SA of nu equals nu, tau becomes a loop, in which case there is an interesting relation. Otherwise there is no, the commutator vanishes. Okay, so I'm sorry? SA of B, so it's the same as, oh sorry, SA of B, it's the symmetry group now acting on the set 1 up to n. So B is, B, the first coefficient parameterizing x's is an integer between 1 and n, so I can act on that as well. So it's the only thing, I mean, that's a sensible thing to do when don't do that. So in a minute I will tell you of a special case when the set I has only one element, and you will these relations are then more familiar. Okay, so we need two more relations. So we know how to commute x's between themselves, x and taus. So now we need to see what we do with taus, and it's the usual bright type relations, really type A. So, and the taus are quadratic operators as well. So this is the first interesting relation. So it tells you that these taus are in general, I mean, the square is, so did I switch? No, that's, wait. Yeah, that's it, wrong way around, thanks. So now we have, what we have here is a loop at mu, okay? You go from mu to SA of nu back to mu. So we have a loop, and this loop is given by a polynomial Q. That's where the polynomial enters, really, evaluated at those two variables. So that's the important relation. So there's some kind of locality there. When you take this product, so the tau messes up somehow position A and A plus 1, and it's expressed in terms of a polynomial involving xa and xa plus 1. And the polynomial you use has to do with the elements of I involved. And now we have commutation relations to B. It's B here. So these are things you would expect that the taus commute if they if A and B are far enough apart. And then there is a last relation, which is a Bread relation of length 3 type Bread relation. So that last relation is a bit complicated, but really it's in some sense it's almost a consequence of that type of relation, and the complicated part. So let me write it, and I will drop the index mu there, otherwise it gets too complicated. And I'll put a 1 nu here to remind you where we start. Okay, so when I wrote tau A, I'm missing a part of the information, okay? I should tell you which vertex should be involved there. But since I multiply by this idempotent on the right, well, the only one where you get non-zero is tau A nu. And then here I should add also A plus 1 and then SA of nu, and then etc. Here it's a more complicated transform. So here tau A is somehow the sum of all tau A mu prime. So somehow, because that makes sense if I is a finite set, but if I is an infinite set, that doesn't make sense. Okay, so that's a quantity that involves again the polynomial Q. So what if you follow the vertices? So you start at mu, you go to SA of mu, then SA plus 1, SA of mu, and then you end up at SA plus 1, SA of mu. And it's the same here, because you have SA plus 1, SA equals SA plus 1, SA plus 1. You have if you replace the taus by the symmetric group transpositions, these two terms are equal. And the quantity you get is going to be 0 in general. So the Bread relation holds. That's when nu A plus 2 is not equal to nu A. So if this quantity here starts at vertex nu and goes to a new vertex where you have switched nu A and nu A plus 2. Okay, this is a transposition. The composition of SA plus 1, SA is a transposition, swapping A plus 2 and A. So if these two are these two elements of I are distinct, then you get 0. Otherwise, you get the following quantity. You get XA plus 2 minus XA inverse times Q nu A plus 1 of XA plus 2 XA plus 1 minus Q nu A plus 1 of XA plus 1. So that's when mu A is mu A plus 2. So when these two vertices agree, these two quantities are now loops at nu. So it makes sense, indeed, to express them as in terms of x's. So everywhere you should really read xa nu, xa plus 1 nu, etc. And you can see that, I mean, these are polynomial. This is a polynomial which is indeed divisible by that. So that whole quantity is a genuine polynomial. So far, there are arbitrary polynomials, yes. I want a diagonal to vanish, which say, for example, that this coefficient here vanishes if nu A is equal to nu A plus 1, which is a case where SA nu equals nu. So if you square tau A nu, in that case, you do get 0. So that's the only requirement I put. Okay, so that's the end of the definition. Okay, maybe I should keep that for a little while. And I will immediately give you an example, a special case. So nu is a vector. Sorry. Nu is a component. Yeah, nu is nu 1 up to nu n. So I will do the case where I has cardinality 1. So an example. So in that case, there is no extra data. Matrix Q is 0. And the algebra Hn of Q, in this case, so Q equals 0 in this case. This is the nil affine Hecke algebra. The set I to the n is also reduced to one element. So it's generated by elements x1, xn, tau 1, tau n minus 1 with certain relations, which you can read off from the black bar on the left, which says that the tau I square to 0, xi and tau j don't always commute. You have to use the formula there, and so xi is commute. And there are gradings as described here. So this term, this you see when Q is 0, this is 0. So it's in this case where I has only one element, we don't have this extra complication. Okay, so these complicated algebras are well behaved under certain conditions on the matrix Q. So what is a good algebra? Well, here we don't have one algebra, we have actually a family of algebra. You can vary the polynomials Q, and you can see if the algebra varies continuously or if you have a flat family. So there are lots of polynomials as above. This is in finite dimensional space, but you can still ask whether this algebra forms a flat family over that space. And the answer is no. And so, but you can look at if there is you can see if there is a part of that space on which there is an interesting part on which it is flat. And that's the case. And flatness, the good case will be when there is a type of a Poincaré-Birkhoff-Witt type property. So one way to express it more concretely is to look for a basis for that algebra. So flat families of algebras mean that you have a basis for the algebra, somehow that's independent of your parameter values. So here we would like to have a basis of the algebra that doesn't depend on the choice of the polynomials Q. And so this is a bit of a mess, these relations, but it's quite easy to see that any element in the algebra you can write as a product of taus times a polynomial in x's. And now I claim that there is a generating family for Hn of Q as a K module. So if you think of a Hecke algebra, so you look at polynomials in X, and then here you have some kind of finite dimensional Hecke algebra, which has a basis parameterized by symmetric group elements. So here it's slightly more tricky because there are cases where the braid relation fails. So you can't really parameterize the basis just by symmetric group elements. You have to make a choice of reduced decompositions for each symmetric group element. Okay, so that's the extra complexity. So given W in Sn, you choose make a choice of say S. Let's say you choose I1, IR in 1 to n, such that W equals SI1, SIR is a reduced decomposition.
1 up to n minus 1.
Thanks. Thank you. Yeah. Is a reduced decomposition of W. And I will denote by curly S the set of, say, I1, IR, or W runs in Sn. So it's a set of these integers. So for each symmetric group element, I've chosen one reduced decomposition, which I want really to think of as a sequence of integers between 1 and n minus 1. And now the generating family is as follows. Okay, I want to keep that for longer. So I define B to B. So I want to take arbitrary products of x's, so monomial in x's, and multiply by a product of taus. So I will take tau. Okay, so with my notations, let's put it this way: tau I1, tau I r times x1 to the a1, x1 to the alpha 1, xn to the alpha n, and then I have to put some nu somewhere, one nu. So again, I've used the short, and so tau indexed some integer really means tau a nu for a certain nu, which you obtain by the one you will get by applying, say, SIR, then SI minus 1, SIR minus 1, etc. of u. So, yeah, I leave it to you if you want to write a more complicated formula. So here the xn should really be an xn nu, x1, x1 nu. And same for tau. So, of course, I mean, if I is finite, that's a sensible thing to do. Otherwise, it's a bit too much. So it's straightforward to see that any element in your algebra you can write like this. You can commute the taus and the x's thanks to these relations, and so you can put all taus on the left. And then you can reduce a big product of tau. You can make it smaller by using these relations and those relations. Of course, when you use a relation like that, you might have some new x's that show up. So you have to push them to the right. But eventually, you get a generating family like that. And now the question is, when is it a basis? And you have the following proposition. That B is a basis. If and only if the matrix Q is a Hermitian with respect to swapping U and V. So here really I should assume that n is at least 2. Because when n equals 1, there isn't enough information in the algebra to get that property. So the algebras that I have defined, Hn of Q, if you restrict yourself to Hermitian matrices Q, they do form a flat family. That's good. We have this big parameter space and tons of algebras which generalize the nil-affine Hecker algebras, which correspond to a one-vertex set. Right, so I would like to now tell you quickly about this realization here. So to prove such a proposition, you have to construct something. I mean, it's not easy to check that a set is a basis. So the classical way to do that for Hecker algebras, is to use the polynomial representation. And inside the polynomial representation, so the fact that the set here is a basis becomes obvious, because it's obvious for certain values of your parameters for which you can, or you know already, this basis property. So you can proceed similarly here. And the key point is to see what is this representation you need to use. I mean, there's so it is always, yes, that's what I said, that it's always a generating family.
Oh, okay.
And that's, I mean, you're just moving the taus on the left and then reducing. So it's fine, yeah. the usual fact. I mean, when you deform algebras, what goes wrong usually is not that the dimension blows up. It's just that the algebra can become 0. Similar here. So it's some kind of symmetry property of the matrix Q, which, from the point of view of Cartan matrices, etc., is quite reasonable to expect some relation between the entries Ij and Ji. Okay, so I need to find the defining relations. The representation. Formula. Okay, so if you think again of the special case where I has cardinality 1, in that case the polynomial representation is on the space of polynomials in the variables x1 up to xn. So there's this usual space of polynomials, and you can write explicitly the representation. I mean, the representation itself is just an induced representation, so you can compute it. And it's similar here. You can define the polynomial representation as an induced representation, and I will tell you directly what it is. So the space is fairly big. So you have to take polynomials, but many copies of them. At each vertex, you have to take polynomials. So at each vertex, we put a polynomial algebra. And now we define an action of Hn on this space. So it should be it should be some kind of quiver representation. If you think of a quiver representation, a representation of a quiver algebra, at each vertex of your quiver, you put a vector space and you put maps between them. So that's exactly what I'm doing. My quiver, as I said at the beginning, is I to the n, and at each vertex, I am putting a big vector space at this space of polynomials. And so the action, well, 1u should act as identity on the new component and 0 elsewhere. So that's the natural thing you do with quiver algebras. Then xi new acts by xi on the new component and 0 elsewhere on the other components. So that's a trivial part. And then the interesting part is the action of tau. And that requires some auxiliary choice. So that representation depends, its definition there depends on an extra choice. So let P be a matrix of polynomials. With Pii equals 0 again. And such that Qij of uv is Pij of uv times Pji of vu. So if you were given such a matrix P, if you define Q with this property, of course Q is Hermitian. But conversely, if you have a Hermitian matrix, you can always find such a matrix P. Well, one way is just to choose, whenever you have an I and a J, to make a choice. You take one of the Pij's to be the Q and the other direction to be equal to 1. Okay, so given Q, you can always find a P like that. But whenever you have a P with this property, that forces your matrix to be Hermitian. So that representation can only be defined when Q is Hermitian. Okay, and so now the action of tau. So tau AV. So Hermitian, there is this automorphism, yeah. So there's an automorphism of K of uv. There's an automorphism that swaps u and v. So I mean Hermitian with respect to this automorphism. That if you, yeah. So that means, yeah, that's this condition Hermitian. Yeah.
How unique is P?
Sorry?
How unique is P?
So the P is not unique, and you can always say multiply by plus or minus 1. I mean, so this is not this is not unique. So later there are some subtleties that will show up not, I mean, really in Q, but in P also. So there are some annoying features there, but for the sake of proving this proposition, it doesn't really matter. Okay, so tau IV is going to go from the component R nu to R SA of nu, and it's 0 elsewhere, and it's given by it's a quite easy formula. It's given by XA minus XA plus 1 inverse times SA minus 1. That's the case where nu A equals nu A plus 1, so say SA of nu equals nu. So in this case, we so nu equals SA of nu. So SA is going to be acts on polynomials on n variable. So 1 is just identity of polynomials on n variables. So that's an endomorphism of the space of polynomials in n variables. There's just one space involved. And when SA of nu is not equal to nu, the formula is the following. We have to take P evaluated at nu A plus 1 in the variable XA plus 1 XI times this reflection. Okay, so the claim, which is straightforward to check, is that if you define endomorphisms of that space as you see here on this blackboard, they satisfy all the relations I've explained earlier. That's just straightforward. You just have to compute both things. And conversely, this representation is faithful, so there are no other relations. R is a faithful representation of Hn of 2. It is as it is for affine Hecker algebra. So in use, you take the subalgebra of the tau-wise, take a one-dimensional representation there, and you induce. So that's the same what you would do for an affine Hecker algebra. You would induce. There's an in representation for the finite dimensional Hecker subalgebra. You induce to the whole algebra. You do get something isomorphic as a vector space to the polynomials. So it's the same, exactly the same construction. You're right. Yeah, it's not so. It's cheating to say that. You're absolutely right. Yeah. So it's a slightly more. I mean, this definition is good. It works. You can think of it as when the I as one element as being induced. In general, indeed, it's more messy because you have when you do this triple braiding that involve X's. So the taus don't form a subalgebra, as Sasha points out.
So the answer is yes or no?
The answer in general is no. You don't have a subalgebra generated by taus. I think you can still write it as a. It's still a natural construction, but it's not. No, it's not so simple. Thanks. Yeah. So that all these things here, what I'm hiding, what I'm not telling you to prove the proposition, is you have to use a filtration on those algebras and pass through the associated graded. And on the associated graded, you have the polynomials Q disappear, and all the relations are then quite straightforward to handle. And you can see that B is the basis, that this representation is faithful, etc. Okay, so that's this family of Hecke algebras that has. So there are two reasons why these algebras are interesting. So one of the reasons is related to what Sasha Keshev explained last week, the fact that they are related to type A affine Hecke algebras, so for special types of Q and I. And the other reason is that certain specialization of those algebras show up in the geometry of quiver varieties. And so here it's some kind of, there's this deformation, this big family, that's quite useful to carry. So that's two general family of algebra for what I will do later. And later I will be talking about Kac-Moody algebras. So if you start with a Cartan matrix, let's call it A, a symmetric Cartan matrix. So a Cartan matrix, symmetric Cartan matrix is a symmetric matrix with values in integers, which has the property that aii is equal to 2 and aij is a non-positive integer if I is not equal to j. So given a matrix like that, so you can you want to see how to get such a Q. So every Cartan matrix is going to lead, or symmetric Cartan matrix is going to lead to such an algebra or family of such algebras. And so we define Q associated with A. So I need to tell you what is the coefficient ring K. So K is going to be a polynomial ring with quite a few variables. And before writing the variables, I'm going to tell you why they are needed. So what I want to do is bound the degree of the polynomials Q according to the entries of the Cartan matrix. So there is a certain coefficient ring K, and then Qij of UV is going to be, so let me simplify, Mij equals minus Aij. So when I is not equal to j, I'm taking for Qij of UV a polynomial of the following type. So I want a polynomial in U and V that has total degree Mij. And I want terms, products of U's and V's, where the coefficient of each of these individual variables is strictly less than Mij. Okay, so I'm looking at the most general possible polynomial with u to the Mij, v to the Mij, and monomials u to the r, v to the s, where both r and s are strictly less than Mij. So I put arbitrary coefficients, except that I do want a term in u to the Mij and a term in v to the Mij. So I do want these two coefficients to be non-zero. That means my ring of coefficients is going to be made of Tij's and their inverses. And of these T, I, J, R, S, where I and J are distinct elements in my set I. And now I need the the matrix to be Hermitian. I need this symmetry property. So, get things right. So. Confused there, but I think I want certain variables to be equal. So I want Tijrs equals Tjisr. I think the other property, if I switch here, if I switch J and I think the other property is okay. So that's almost good. You just have to be careful that if Mij is equal to 0, then it's not quite right what we're doing here, because we're using Tij. Tji, I mean, it appears twice. That's not good. So, and so that's for Mij non-zero. And if Mij is 0, you have to take Qij of uv to be equal to Tij. And I think I want also, yeah, so I think also this property Tij for Tji. So these two properties will ensure that my polynomials Q are satisfy this Hermitian property, my matrix of polynomials. And so the point is take a polynomial as general as possible with these leading coefficients and smaller monomials. Okay, so that leads to an algebra Hn of A, you want. So given a Cartan matrix, we get an algebra which depends on a certain number of parameters, but now only finitely many parameters. If the set I is finite, at least, there are finitely many parameters. And the last thing I want to do before finishing today is to tell you what does appear when you look at quiver varieties, or what does appear when you look at affine ecoalgebras of type A, and try to view them in terms of those algebras. So you end up with no more variables. So the variables disappear. So it's a certain specialization of those polynomials. SR, it's an S, I'm sorry. Okay, so final thing is about the relation, what will come eventually with covarieties, and how to get specializations to get Qij really as a polynomial over Z. And I don't want these XY indeterminates. So quiver varieties are set not just with a Cartan matrix, but with a quiver, as the name says. So a Cartan matrix is the same as a graph. Okay, so Cartan matrix is the same as a graph with vertex set I and with Mij edges from between I and J, and no loop. So that's the same data. Given a symmetric Cartan matrix or a graph, it's the same thing. So now we want to put an orientation on the graph, and given an orientation, I'm going to define a specialization of those polynomials. So given an orientation of that graph, so we define now a specialization of those polynomials. And so Qij now is defined as u minus, minus 1 to the number of edges from I to j times u minus v to the Mij. So So the dependence in the quiver is minor. It's just in the sign. So this depends only on the graph, and so we get an algebra, say Hn of gamma. So where gamma is the quiver above here. So when you start with a quiver, which has a number of whose underlying graph defines a given Cartan matrix, a given symmetric Cartan matrix, then you can define certain polynomials, Qij, like this, and you can define algebras, and these algebras will occur in the last lecture when you consider perversives on Lustig's quiver varieties. So these algebras are very natural from this point of view, and so all these complicated relations, in this particular case, I mean, they just come from the geometry. There's no magic. I mean, finding these relations, just compute them in the geometry. So last thing I should say is that these algebras, so you have many parameters, and in general, these algebras are not graded. The relations are not homogeneous. But in this case here, the polynomial Q is homogeneous, and this becomes graded. So Hn gamma is a graded algebra, whereas the degree of the xi's, xa is equal to, the degree of xa is equal to 2, and degree of tau a nu is equal to m nu a plus 1, sorry, equal to is a Cartan number, so it's minus. I need to check that now. So you do get, in general, grading. Okay, is it plus or minus? Now I have a dot. No, I think it's, I think it is plus. No minus sign. So for example, when nu a equals nu a plus 1, you get one of the diagonal terms. It's the opposite of the Cartan in tree, so it's minus 2, for example. When nu a equals nu a plus 1, degree of tau is minus 2. In general, it's going to be a positive degree. Okay, so that's all for today. So these algebras, they should have occurred in, or similar versions, probably occurred in Shakleshev's talk, when the quiver is as a affine type A. So for general quivers, Kovanov and Lauda have introduced other specializations. So they've introduced independently specializations of these algebras where they have no signs. I mean, they work purely combinatorially. So they use no sign here. And instead of u minus v to the mij, they use u to the mij plus v to the mij. So when mij's are equal to 1, there's only a sign difference with this definition here. But in general, it's, these are quite different algebras. So they have these algebras for which they encode the defining relations by using some kind of diagrams with breadth. Okay, so that's all for today. So tomorrow I will introduce some categories that build on these algebras.
Thank you very much. Are there questions?
Just a quick question. You say that for the special case, q to the ij is some sign of u minus v to the mij. When mij is odd, that gives a u to the mij with a plus sign and a v to the mij with a minus sign, and that doesn't seem to be a specialization where tij is equal to tki.
Yeah, I think you probably I should drop that one. Yeah, thanks. So that's probably a relation. Sorry, in my notes, I don't remember. In my notes, I wasn't clear. So, that's possibly only when it seems that it's needed. Symmetry is automatic here, so I think it's only needed when mij equals 0. Thanks. So I mean that's probably should should be too difficult to see that that's all you need to get the symmetry property, and otherwise your remark probably shows that. Otherwise I lose this. Thanks.
Further questions or remarks? And let's thank all the speakers of this morning again.